As with any other technique for calculating integrals, with trigonometric substitutions, you might need to combine them with other tricks for calculating integrals. You never know what's going to happen. You might need to use a trigonometric substitution and then integration by parts, or a u substitution and then trigonometric substitution. It's hard to tell at the beginning what's going to end up happening when you actually calculate an integral. So let's see an example of the sort of thing that can happen. So with this one, when I look at this integral, I don't immediately think trigonometric substitution, because it's true that we have a power of 1/2 here, actually 3/2, but you know, it has a factor of 1/2. But this thing that we have to the power of 1/2, it's not a perfect square, or I'm sorry, it's not a sum of squares, and it's not a difference of squares either. So at first it doesn't appear like a trigonometric substitution is going to be useful. But, right, this is quadratic, right? The stuff in parentheses is quadratic. And one thing you can do with quadratics is you can always complete the square. Completing the square with a quadratic will always turn the quadratic into either a sum of squares or a difference of squares. So even though it's not written as a sum or difference of squares right now, if we complete the square, it will be. And then we could use a trigonometric substitution. So let's do that. Let's go ahead and complete the square in the denominator here. The numerator we're going to leave alone for the time being. Let's see, when we complete the square, I guess let's factor out that -4. That gives us x squared plus x here to the 3/2. So to complete the square, we need, inside these parentheses, we need an x squared plus x plus a quarter, right? Yes, minus a quarter, right? Plus a quarter, minus a quarter. That's how you complete the square. To the 3/2 dx. Integral of x squared over 3 minus 4 times. Now inside these parentheses, right, these first three pieces should be a perfect square. These should be x plus 1/2 squared, which they are, minus 1 over 4. Let's distribute this 4 here like that. So that's going to make this plus 1. Right? Yeah. Okay. All to the 3/2 dx. So x squared over 5 minus 4 times x plus 1/2 squared. Sorry, not 5, 4. To the 3/2 dx. All right. Having this 4 here, let's factor this out here. So factor it out. We get the integral of x squared over, so when we factor this 4 out of the denominator, this exponent hits it. So 4 to the 3/2, let's see, 4 to the 1/2 is 2, to the third is 8, so 8 times, the stuff that's left over when we factor out that 4 is 1 minus x plus 1/2 squared to the 3/2 dx. All right. Now it looks more like something we would want to do a trigonometric substitution with, except instead of just taking x equals for our trigonometric substitution, right, because the variable part is squared and it's a difference of squares, we're going to use sine theta, and with a 1 in front because of this 1 here. But it's not just x that's squared, it's x plus 1/2, so we need a plus 1/2 right here. Okay. Now when you take differentials on both sides, this constant 1/2 does go away. So differential on the left-hand side is just dx. On the right-hand side, it's cosine theta d theta. And now we can do our substitution. So integral of, let's see, one unfortunate part about this is to do the substitution right? We have to deal with this x squared in the numerator, we have to move this 1/2 over. So x squared is sine theta minus 1/2 squared over 8 times 1 minus sine squared theta to the 3/2 d theta integral of, so I'm going to leave the numerator alone for the time being, so sine theta minus 1/2 squared, let's see, move that 1/8 outside. In the denominator, 1 minus sine squared is cosine squared, but cosine squared to the 1/2 is just cosine, so we get cosine cubed down here. Oh, I've made a mistake. This cosine that's part of dx, I left it out, so it should be here, and that means in this last line we have cosine theta d theta. All right, now we can cancel a factor of cosine, and we get 1/8 times the integral of sine theta minus 1/2 squared over cosine, this should be cosine squared theta, right? D theta. Okay. So, how to handle this, right? The question with this with any substitution is, did it help? Did you make your life any easier by doing this substitution? For this substitution, let's see, we haven't quite run out of tricks to try out yet with this trigonometric part, because we could multiply out the numerator. So if we multiply out the numerator, we get, so we've got a 1/8 in front. Multiplying out the numerator, we've got sine squared theta. We've got minus sine theta, sorry. My brain stopped working there for a second. Yes. Plus 1/4 all over cosine squared theta d theta. So what to do here? Well, you know, this denominator really divides each piece in the numerator, and each individual piece looks doable. So what we're integrating is sine squared theta over cosine squared theta minus sine theta over cosine squared theta plus 1/4 cosine squared theta, all d theta. And each piece looks doable. Now the tricky thing is how we do each piece is going to be different. So for the first piece, so let's treat each of these as a separate integral. For this first piece, this is tangent squared, right? Sine squared over cosine squared is tangent squared. And you may have seen tangent squared before, the integral of tangent squared before. The way to handle that is to turn it into secants. So this is secant squared theta minus 1. Okay, for the integral of sine over cosine squared, this is set up for a u substitution. So we'll let u be cosine theta. So that means du is minus sine theta d theta. So, right, this minus sign turns this into a plus, and we get 1/u squared du plus integral of 1/4, let's see, cosine squared is secant squared theta d theta, right? And now we're almost there, right? Each piece we can integrate. In fact, we could combine some of these pieces. I won't, just because I don't feel like it right now. Integral of secant squared is tangent. Sorry, I'm integrating. I don't need to write the integral symbol again. Integral of secant squared is tangent theta minus integral of 1 with respect to theta is 1. Right? Be careful when your integrals have different variables that when you integrate a constant, you end up with the correct variables. So integral of 1 with respect to theta is 1, or is theta, sorry, plus integral of 1/u squared is minus 1/u plus 1 over 4 times integral of secant squared is tangent theta plus a constant. Okay, now the tricky thing about this is, remember, we need to get back to the original variable. So we have a mix of substitutions here. We had a u substitution, so let's undo that. I guess first we should combine these tangents. So here's 1/4 times tangent, here's another tangent, so altogether that's 5/4 tangent. Okay, so 5 over 4 times tangent of theta minus 1 over u, but u is, right, u is cosine theta, so 1 over u is secant theta plus a constant. And now we need to undo our trigonometric substitution, which I don't even remember what it was, it's so long ago. X plus a half is sine theta. Okay, so x plus a half is sine theta. So to undo this substitution, right, let's draw one of our right triangles. Theta over here. So sine is opposite over hypotenuse, so we need a 1 in our hypotenuse, and x plus a half on the opposite side, so the adjacent side is the square root of 1 minus x plus 1/2 squared. Okay, so 1/8 times 5 over 4 times tangent, which is opposite over adjacent, so x plus a half over square root 1 minus x plus a half squared, minus theta, which, right, we just have to solve our substitution equation for theta, so that's inverse sine of x plus a half, minus, and then secant theta is hypotenuse over adjacent, so 1 over the square root of 1 minus x plus a half squared. All plus a constant. Okay, so you can see that even tricky integrals, if you just take them step by step and at every stage just sort of think about what plausible techniques of integration you might use, you can solve even very complicated integrals.